Okay, good morning, folks. Looks like we've got a quorum online, so maybe let's go ahead and get started. Can you hear me okay? Video's coming through? Everything's focused enough?
Yes.
Okay, good. Let me turn up the volume a little so I can hear you a little bit better. Okay, not much to discuss in the way of logistics. Mostly, I want to make sure that everyone is aware that I have to insert a cutoff on homework acceptance this Friday, the 5th. So that is your last chance to get in all back homeworks that are due before I release the solutions so that you have them for study material. I have a couple that I didn't get around to grading this weekend, but these are the totals that I have in my possession right now as far as submitted homework. So homework number 3, I have 11 out of 14. Homework number 4, I have 4 out of 14. Homework number 5 is not due until this Friday, but I only have 1 out of 14. So if you would like to make sure that you get these submitted in time without having to take a 0 initially and then maybe make up to half of lost points with corrections, you need to get them in by this Friday, please. The purpose of this is, of course, that we are anticipating the midterm next week. So my plan is Monday, a week from today, we will go over the sample exam in class. I want to make sure that you have a copy of what the exam will look like, how I plan to format it, what will be expected of you. We will solve it in class on Monday. So this Friday at the end of the night, I will post all solutions on Canvas so that you can take a look at them over the weekend. We will review in class on Monday, and I expect the midterm to be a week from Wednesday. That would be the 10th. So like I said before, my plan is to hold this in class. That does not mean you need to be physically here in the room. If you would like to be, you are welcome to be. If you would like to be online, the exam will appear on Canvas at the start of class. You can download it, work on it, and then I will give you an extra, 30 minutes or something after the end of class to upload your solutions to Canvas. So I think we've talked about everything else as far as the midterm, what I anticipate to be on it. The purpose of having it in class is mostly to constrain me so that I cannot give you anything too long or too complicated if the entire thing needs to be solved in an hour and 15 minutes. So I'm anticipating mostly conceptual questions, simple computations, fragments of proofs, not anything long and involved like you've seen in the second problems of the homework. I think this is one thing that I had not mentioned before that I want to make explicitly clear now. I intend the midterm to be open notes, open textbook, open to everything except collaboration with other people. So you can use your textbook, you can use your notes. If you have a problem and it rings a bell that says, oh, I need to use that formula, you can look up the formula. You don't have to have that stuff memorized, but know where to find it on a quick basis, but be prepared to work through everything yourself. That's it as far as logistics on my end. You guys have any comments or questions before we get started on physics?
When you say open book, is that just Shankar? Or can we also use other textbooks?
So you can use your notes, you can use Shankar. If you have Griffiths or some other textbook that you want to look stuff up in, that's fine. If you want to Google stuff on Wikipedia, I don't care too much about that. But I want you to work independently and write your own solutions. Okay?
If we use outside sources, would you like us to cite them?
It would be helpful for me, but I'm not going to police you about it.
Okay.
Certainly not going to do any lockdown browser crazy stuff like that. Yeah, it would be helpful for my own purposes if you say, hey, I know there was a useful formula about this in Griffiths, then I can better follow your train of thought and understand what you're doing. But I'm not going to be authoritarian about it.
Okay, thank you.
Okay, if there's nothing else in terms of logistics and class stuff, then let's recap what we've been talking about last week. We've been taking our time to work through perturbation theory because this is something that I think is a genuinely new concept for many people, and it's tough to wrap your head intuitively around what's being done. So the main formulas that we derived were these ones here at the bottom of the board. This is the stuff that you will need to use and apply on homeworks and exams and things. But we spent a lot of time talking about where it comes from to try and help you understand it and wrap your head around it. The main idea of perturbation theory is that the eigenvalue problem is nonlinear. So if you take your Hamiltonian, your original Hamiltonian, and you modify it slightly, that slight deviation as implemented by a small perturbation with some numerically small coupling constant and a new Hamiltonian, that small linear deviation of the Hamiltonian operator produces a whole nonlinear response from the eigenvalue problem. And so the idea is to linearize the nonlinear problem and solve it systematically order by order in the small coupling constant. So we talked about the 0th order solution, 1st order in perturbation theory, 2nd order in perturbation theory. The main formulas that you need to apply on homework 5 and for the exam are 1st order shift in the energy. The 1st order shift in the energy is just the expectation value of the perturbation itself. So anything which is diagonal, that starts you off in one state and leaves you at the end of the day in the same state, acts like a shift in the energy. With exactly one insertion of the interacting Hamiltonian, there's only one thing that you can do. You start off in one state, you get hit by that perturbation, you stay in the same state. That's the 1st order shift in the energy. At 2nd order, now you have for the first time the ability to jump from one level to a different level and then jump back. So that's how you end up with something that is quadratic in the perturbation. You start at the state n, you jump to any other state m which is different from n, and then you jump back to n. That happens on a characteristic time scale. The time scale is 1 over the energy denominator. The energy denominator is the energy you have, En, the state you're starting with, minus the energy you want to make that temporary quantum fluctuation, En. That difference could be positive or negative depending on whether you're jumping up or whether you're jumping down. And that determines the shift in the energy. One consequence of this was that the energy shift of the ground state is always negative. You have sort of a downward pressure from all the states above and an upward pressure from all the states below. So the ceiling state always goes up in 2nd order perturbation theory. The floor state always goes down. For the correction to the eigenstates, the eigenfunctions, we only looked at that at 1st order. This is all you'll really need to reproduce under pressure. That 1st order correction to the wave function, again, reflects one jump from the state n you start off with, one insertion of the interacting Hamiltonian to any other state m. And again, that happens with a characteristic time scale characterized by the energy denominator. In principle, there can be a correction or a possibility from the dressed state to land you back in the original state. At 1st order in perturbation theory, this can be set to 0. Eventually, later orders in perturbation theory, that's not the case. But for your purposes on reproducing things under pressure, that has 0 overlap with the original state. And I tried to give you some intuitive picture from the time dependence that comes out of this. It takes a lot of very powerful machinery to derive the time evolution operator in the full theory. This involves a transformation to the interaction picture, which is really the most efficient way of really calculating higher order corrections in perturbation theory. But what you get coming out of it is something very intuitive about what your perturbation is doing. The perturbation series is a series in the number of insertions of that interaction. At 0th order, your time dependence is just the bare time evolution, u0, from some initial time to some final time, which you can represent graphically. At 1st order in perturbation theory, that is the origin of this formula and this formula. There is exactly one insertion of the perturbation. You have free propagation, where your state is just minding its own business. Suddenly it gets hit by a car with the perturbation. And then maybe it transitions to a different state, maybe it stays in the same one, but you have exactly one insertion in the entire history of this thing. 2nd order in the perturbation series is exactly 2 insertions where you can now transition and then transition back. And as you go to higher and higher orders, you continue to build a more complicated time dependence with further and further insertions of the interacting Hamiltonian. Okay, any questions on what we talked about last week before we talk today about the limitations of perturbation theory?
I think the only comment that I have is there on the graphs on the right, when the Hamiltonian and the energies get in smaller in font, the subscripts and superscripts are kind of hard to read.
Sure. Yeah, sorry for the squeeze over here. I hope the correspondence is clear. The thin line is always bare propagation u0, and then you have the crosses, which are all of the insertions of the interacting Hamiltonian.
Okay.
Yes, point taken. I don't think it's super important for this, but if anything else gets too small to read, please interrupt me and I'll make it bigger. Okay, at the end of class last time, we worked through a simple example of how to use these formulas. We did a 2-level system, which was actually somehow a problem that was on the comprehensive exam in 2017. There's another simple example that's worked out nicely in the textbook that I wanted to work through, which is a linear deviation to the harmonic oscillator. So this will start lecture 10. Limitations of perturbation theory. So let's work through another example before we talk about these limitations. This is the harmonic oscillator with a constant force. So my bare Hamiltonian H naught is the usual harmonic oscillator, p squared over 2m plus 1/2 m omega squared x squared. And the perturbation that I'm going to add to a GH1 is just a constant force. So let me add a constant force, just some number, and that's linearly proportional to the position operator. So this does a certain amount of work, F times x on the system. So as we will see, this corresponds to a displaced harmonic oscillator. It's like a spring hanging down under the influence of gravity displaces by some fixed amount, and then it oscillates just like normal. That's what we will find for the quantum harmonic oscillator. All right, so let's remind ourselves what the eigenstates and the eigenvalues were of H naught. So it's zeroth order in perturbation theory. What we found were that the bare energies En0 were n plus 1/2 h bar omega, the standard energies of the harmonic oscillator, and the eigenfunctions n, written in a position basis at n and x, had some Gaussian asymptotics, and they had a polynomial piece that was given in terms of the Hermite polynomials. So there was some overall coefficient that I don't care enough to write out. I'll just call it Cn. The Gaussian piece was e to the minus 1/2 m omega squared over h bar x squared. And then you have the Hermite polynomials hn with argument square root m omega over h bar x. So these were our unperturbed states, and we want to find the influence on these things coming from the linear perturbation, the linear force, which is proportional to x. So let's calculate the first order shift in the energies. GEN1 is the expectation value in the bare states of the perturbation. The perturbation is a constant f times the position operator. So I have harmonic oscillator states n, and I have a position operator sandwiched in between. What's the first thing that should be ringing in your head that I should do? I don't want to evaluate x in these things. I want to change x into something else. What is the something else?
Ladder operators?
Ladder operators, A and A dagger. So I quickly look up in my textbook to figure out what the formula is with the correct coefficients. And I find that this is f times the square root h bar of 2m omega n a plus a dagger n. A and A dagger, I know how to act on these states. A dagger raises it, A lowers it. So clearly, if A dagger turns n into n plus 1 and A turns n into n minus 1, then the first order shift in the energy is 0.
Well, can you repeat that last bit again?
Sure. So we know that A dagger acting on n is proportional to n plus 1. We know that A acting on n is proportional to n minus 1. There's some coefficients, but those don't matter for this because I have n and something different than n. Because the state we're talking about, you jump up by 1, you jump down by 1, you could not stay in the same state. So at first order, you must change states away from n. You have 0 probability to stay in the same n. So there is no shift in the energy. So second order in perturbation theory is the first contribution that will be non-zero. So at second order in perturbation theory, G squared En2, this is the sum over all states M different from N. Expectation value, M0, GH1, N0. Sorry for squeezing this in the corner here. En0 minus Em0. Hopefully this is clear. So this is the same. N goes to M, modulus squared, over En minus Em. So in this case, I have sum over all M different from N, 1 over. I know what these energies are. In the denominator, this is N plus 1/2 H bar omega minus M plus 1/2 H bar omega. This is the denominator plugging in for these energies. My numerator is just M0 Fx N0 squared. So again, F is a constant. I can simplify the denominator a little bit. The plus 1/2 cancels out. That's the same for both of these things. And there's an overall H bar omega. All right, so in the denominator, I have N minus M, sum prime over all M different from N. I have 1 over N minus M, H bar omega. My numerator, I have F squared. And the matrix element that I need to calculate is the modulus squared of M0 X squared. M0 X N0 modulus squared. There we go, that's better. Now I'm going from N to a different state M. And now I'm not going to get 0. So what do I get? So if I plug in again for X, I have square root H bar over 2M omega, and now I've got 2 of them. So I have H bar over 2M omega, and now I have M0 A plus A dagger, N0 squared. So before I got 0, because I demanded that I start in state N and I end in state N, which is the same as the one that I started off with. Now I'm going to get something non-zero because I can jump from N to a different state. So first I will evaluate A dagger acting on N. A dagger acting on N gives me a square root of N plus 1, and then the state N plus 1, I'll put parentheses and a 0 on it to indicate that these are still the bare states. A acting on the state N gives me square root N times the state N minus 1. So this changes the state, and I only get a contribution if M is either N plus 1 or M is N minus 1. So by using this action of the raising and lowering operators, I can say M naught GH1, or let me put it this way, M naught X, A plus A dagger, excuse me. Let's do it this way. So this number is either a Kronecker delta with M equal to N plus 1. And in that case, the number that I get is square root N plus 1. Or it's a Kronecker delta M N minus 1. And in that case, the number is square root N. So is it clear what I did here? I have this matrix element, A dagger acting on N gives me square root N plus 1. And then I had N plus 1 M. This thing is this Kronecker delta. If I have A acting on N, I get N minus 1. This thing is a Kronecker delta that sets M equal to N minus 1. So I get 2 terms, and then I'm going to square it. All right, so altogether I have sum over all m different from n, f squared over m minus n, and then I have, let's see, I can cancel one factor of h bar, and I have 1 over 2 m omega squared. So inside that set of parentheses, I have Kronecker delta m, n plus 1 times square root n plus 1, plus Kronecker delta m, n minus 1, square root n. And I've got to take that thing and square it. Yes, sir. Did I mess something up?
Those two m's are different, right? One corresponds to the mass
yes,
and one
thank
is
you.
one to the
Yeah, so this is the mass. Apologies. Maybe let me call this capital M for a moment. We'll finish up the sum over M. Thank you. Yes, this is the mass M, and that's not the same as this index of summation. Okay, when I square it, I'm only going to get 2 terms. There can't be any cross terms between these 2 things because these are mutually exclusive. I will have, if you like, delta m, n plus 1, square root n plus 1 squared, plus, if you wanted, there would be a cross term, delta m, n plus 1, delta m, n minus 1, square root n plus 1, plus delta m, n minus 1, square root n squared, if I just sort of blindly open up the parentheses. Of course, this cross term is 0. These Kronecker deltas are mutually exclusive. M cannot both be n plus 1 and n minus 1 at the same time. So that thing is 0. Kronecker delta is a number that's either 0 or 1. So when you square it, nothing happens. So this is the same thing as delta m, n plus 1 times n plus 1. You square the factor. And likewise, this is Kronecker delta m, n minus 1, and you square the factor. So I've only got 2 contributions to this sum. Either m equals n plus 1, and I get this number, and I've got to remember to plug it in down here too. Or I have m equals n minus 1, and I've got to plug in that number down here as well. So altogether, I have a prefactor, which is f squared over 2 times the mass times the frequency squared, times, now I've got 2 cases. The first term, I have n plus 1 over m equals n plus 1 minus n. And from the second term, I have plus n, and the denominator is m equals n minus 1 minus n. Okay, so altogether, I have f squared over 2m omega squared. This first term, n plus 1 over positive 1, I'm going to leave just like this, plus n over negative 1. These 2 terms were the terms that were associated with either a jump that takes me up a level or a jump that takes me down a level. So if I were going to draw a picture about what's happening, I would have my ladder of states. If this is my quantum state n, and this is n plus 1, and this is n minus 1, I start off in the state n0. I'm making 2 jumps that have to end me back at n0. So I can jump up a level and then down a level. That's this term. Or I went from n up to n plus 1 and then back down to n. That first term corresponds to this correction to the energy. This is a positive correction to the energy. That is not what it should be because I wrote this factor backwards. Should be the energy I have minus the energy I want. That's why I'm getting the wrong sign here. You should see a downward pressure from all the states above. So my apologies. This is why it's good to do a check like this. So this is n minus n plus 1. And this is n minus n minus 1. There we go. So what I should get is I should get something which is negative from this term. From the contribution where I jump to a state above, that's going to lower the energy. So I should get a negative shift to the energy from jumping up a level and then back. On the other hand, if I jump down a level, n minus m, now I get n minus 1, that's a positive contribution. If I jump down a level and then back up, that's this term, which corresponds to this contribution to the energy. So the level below, the probability to jump to a lower energy state pushes the energy up. The probability to jump to a higher energy state pushes the energy down. So there is a competition between these two pressures, a downward pressure from the higher state and upward pressure from the lower state. Whichever one wins is determined by those coefficients, whichever it is more likely to jump to. In this case, it is more likely to jump up than down. So that overall gives you a negative contribution, which wins out. Apologies for the n and the m interchange. It's easy to make that mistake, so it's always good to do a quick physics check at the end. Okay, so what this gives me is the second order energy shift is overall positive. Why do I have positive here? It looks like it's negative. Negative f squared over 2m omega squared. That looks like a mistake in my notes online. Yeah, so clearly the downward pressure from the upper state wins. So I should get a negative shift in the energies. Okay, sorry for fumbling on this a little bit. I hope this is clear now that I've corrected the signs. So what is the effect on the states? At first order, we can calculate the correction Gn1, which is the sum over all m different from n, and then I have the overlap onto the state m. GH1n over En minus Em. I think when I first wrote this on the board this morning, I didn't put that the ket state here, the M. Of course, these are a set of quantum states, so there should always be a ket here. Okay, so we're going to plug in the same amplitude that we had before. The answer is the same. So I'm going to get sum prime, all m different from n. I have the state m0. This one is going to give me a square root of h bar over 2m omega and a factor f. So then I'm going to have m0, a plus a dagger, n0 over n plus 1/2 h bar omega minus m plus 1/2. H bar omega. All right, so as before, the halves cancel. All right, so I get Gn1 is, I have f square root h bar over 2m omega. I'm going to have a 1 over h bar omega coming from that energy denominator. I have a sum over all m different from n, the state m, and then upstairs I have ma plus a dagger n, and then divided by n minus m. So now I plug in the action of the raising and lowering operators, and I get f square root h bar over 2m omega, 1 over h bar omega, and there's only two contributions here. I have the n plus 1 combination, and that one came with square root n plus 1 over n minus n plus 1. The second state is n minus 1. And for this downward jump, I have square root n over n minus 1. Okay, now the signs are working out as they should. I get a negative energy denominator from jumping up. I get a positive energy denominator from jumping down. So this one is minus 1. This one is plus 1. So altogether, if I group these coefficients, I have, let's say, f over square root 2m h bar omega cubed times n plus 1 square root n plus 1 times the state n plus 1 minus square root n times the state n minus 1. Except I put my minus in the wrong place. The minus sign is on the first term. I had a minus sign from jumping up, so the n plus 1 comes with the minus sign. I had a plus 1 from jumping down, so n minus 1 comes with a positive sign. Okay, so we found the correction to the wave function, and we found the correction to the energies. What does it all mean? Is this even right, or did I fumble it too many times to even tell? This is nice because this is a problem that you can also solve exactly and then compare with the answer you get in perturbation theory. So the total Hamiltonian that we had from adding the bare plus the correction was p squared over 2m plus 1/2 m omega squared x squared, now plus a linear correction, f times x. We can solve this exactly by completing the square and casting it back into a form that looks again like a quadratic potential. So if I pull out some common factors, this is p squared over 2m plus 1/2 m omega squared times, this is x squared plus 2f over m omega squared x. And now I can strategically add and subtract the missing term to complete the square. So if I strategically add f squared over n squared omega fourth times 1, I guess, and subtract the same thing, this piece together, if I added and subtracted correctly, should be x plus f over m omega squared squared. And the other one is just a constant. So what I end up with is h is p squared over 2m plus 1/2 m omega squared times the displaced harmonic oscillator, x plus f over m omega squared squared, and a constant coming from that minus sign, minus f squared over 2m omega squared. So if this is my harmonic oscillator, I already know the answer. This looks exactly like a regular harmonic oscillator with two effects. I have a shift in the origin of coordinates. So before, what I had was x squared is now x plus f over m omega squared. So this is a shift to the left, minus f over m omega squared. The other effect is I have a constant shift in the energies. this number should look familiar, even including the minus sign that I fumbled the first time. This was exactly what we calculated as the second order shift in perturbation theory, minus f squared over 2m omega squared. So that second order perturbation theory correction to the energies is exact in this case. So there are no further corrections to the energies from higher orders in perturbation theory. I can immediately write down the energies from this displaced harmonic oscillator as n plus 1/2 h bar omega minus f over 2m omega squared. For the effect on the eigenfunctions, that's harder to interpret, but it all comes down to this shift. The statement is that my wave function is shifted, so that my new eigenstates n are just a translation operator. So let me write the translation operator with a displacement of maybe let me write it this way, put it directly in the position basis first. So the effect is the thing that used to be called x is now called x plus f over m omega squared. So if n0 was my original solution to the original Hamiltonian p squared over 2m plus 1/2 m omega squared x squared, that one at position x plus f over m omega squared is equal to the answer for the new corrected Hamiltonian at x. So this is just a shift in coordinates. I can write this as a translation operator. So this is the translation operator acting on the state x. This is t dagger of f over m omega squared. So the dagger, because it's acting to the left on the bra, the shift is going from x to x plus f over m omega squared. So now if I write in what that operator is, x, this is e to the minus I over h bar. That's the translation operator. Since it's dagger, that becomes plus. The distance is f over m omega squared, and the generator is momentum, p. So I'm writing down what the translation operator is. Let me remind you. Let's say t of a was e to the minus I over h bar a times the momentum operator p. I'm plugging in for that here, but now I have t dagger. So e to the minus I becomes e to the plus I, and the displacement is f over m omega squared. So we believe this is the exact formula for the corrected eigenfunctions, that n is becoming the original one times this translation operator. If we evaluate this to first order in perturbation theory, we can compare with the answer we had. So there is a constant shift in the energies and displacement of the wave function. So let me write n equals the translation operator e to the plus I over h bar f over m omega squared p acting on the original state n naught. So let's evaluate this to first order in perturbation theory and compare. So at 0th order, this exponential is just 1. So this is n naught. Plus first order in perturbation theory is I over h bar f over m omega squared, momentum operator acting on the state n. Now, I don't know how to immediately act momentum operator on the state n, but what should I do? What do I do to p to write it in a form that I know how to act on n?
Change it into the ladder operators again?
Into ladder operators. This is the counterpart to x. So this is plus higher orders plus order f squared. And I plug in for the momentum operator. I have have I over h bar F over m omega squared. The momentum operator is I square root m omega h bar over 2. And then now this is a dagger minus a acting on the state n. So overall, let's see, I have I and another I that gives me a factor of -1. So I have minus F, let's see, I have m downstairs and square root m upstairs. So that's a square root of m downstairs. I have a square root of 2 downstairs. I had h bar downstairs, square root h bar upstairs. So that's one factor of h bar inside the square root downstairs. I have omega cubed here and square root omega upstairs. So that is 1 over omega cubed inside the square root. And now from the parentheses, I have a dagger acting on n0 is square root n plus 1, n plus 1, 0, minus a acting on the state n is square root n, n minus 1, 0. And if I compare this with what we got in perturbation theory, assuming that I didn't fumble any more signs, this should agree with the first order calculation. Let's see, f over 2m h bar omega cubed inside a square root. And if I distribute the minus sign, I get a negative correction going to n plus 1 with square root n plus 1, and an overall positive correction going to n minus 1 with square root n. So this agrees with perturbation theory. Okay, so this was a bit more complicated of an example than the two-level system that we worked out last time. Here, there, you had a whole ladder of states that you could jump to. In this case, because you had a dagger and a, the only choices were to jump up one level or down one level. In other more complicated Hamiltonians, there can be many possible jumps. In this case, there were only 2. But hopefully this serves to illustrate the physics of the downward pressure on the energy from states above, the upward pressure on the energy from states below. And you can compare that with the exact solutions in certain problems where an exact solution is available. Okay, any questions on this example? Okay. So in the remaining half an hour, I want to talk about what the assumptions and limitations of perturbation theory are. Perturbation theory is a fantastic tool. Honestly, I think it gets a bad rap. Perturbation theory is one of the few systematic tools that we have that allow you to control your uncertainty order by order. But it has a number of assumptions built into it, and any or all of them can be broken in very important ways. So first is the assumption that there is a one-to-one correspondence between the eigenstates of the bare Hamiltonian and the dressed one. H0 and H full. So that you can talk about the energy of the bare state in some level n and associate that with a correction to the energy of that level n. You don't have some doubling of the states or something where you don't know what to compare the original state n to. And likewise, it's meaningful to talk about the original wave function n and a correction to that wave function n of the same state. So there has to be some kind of one-to-one correspondence so that you can talk about a state before and after the perturbation. Second assumption is that you need the eigenstates and the eigenvalues that come out of this to be smooth functions of the coupling constant. eigenvalues and eigenfunctions depend smoothly on the coupling constant G. That smooth analytic dependence is what's supposed to make it possible to perform a series expansion. So that then I can talk about the corrected energy En depends on the coupling constant. And I can expand that dependence in a way which is something which is constant, plus a linear correction in G, plus a quadratic correction in G, and so on. And likewise corrections to the state, N, which depends smoothly on G, in a way that can be expanded in a series. Third assumption is that the coupling constant is sufficiently small that the series converges, and you can justify truncating it at finite order. So these are the assumptions that underlie perturbation theory. Any and all of them can be broken, and I want to talk about the cases when that happens and what it's telling us. All right, so let's walk through a few different scenarios of how things can go wrong. Scenario number one, the coupling constant is not very small. So the illustrative comparison here is between quantum electrodynamics, where the coupling constant is the fine structure constant. So QED is a field theory of quantum electrodynamics. And in this theory, the coupling constant is related to the electron charge, and the electron charge squared is related to the fine structure constant. So in this theory, the relevant coupling constant is alpha ENM, which has a nicely small value of about 1/137. So in this theory, the coupling constant is excellently small. So I can describe a quantum state of an electron as being a bare electron in a non-interacting theory, plus a correction where the electron splits into an electron and a photon, plus another correction where the electron splits into an electron and two photons, plus another correction where the electron splits into a photon and that photon splits into another electron-positron pair. And so on and so forth. In principle, all of these things are corrections that can happen in perturbation theory whenever I add in a perturbative interaction generated by the coupling of that electric charge to the electromagnetic field. Every time I insert one other vertex here, that is one other insertion of the electromagnetic interacting Hamiltonian. But because the coupling constant in QED is so beautifully small, there is a well-controlled approximation that I can say this is 0th order, this is one insertion, this is a 1st order correction. These are a set of 2nd order corrections. And so on. In principle, I have a whole nasty series of quantum fluctuations. Everything that can happen does happen in quantum mechanics. But because the coupling is small, I can get away with a nice approximation in perturbation theory that is well controlled and nicely describes data. And only if I need to really do precision measurements down to many, many decimal places do I have to worry about second and third order corrections in QED. That contrasts very strongly with the nuclear force. The strong nuclear force goes by the name of quantum chromodynamics. QCD, for reasons that I will not get into now. You can write down a picture which is very similar. It's a theory in which you have a quark, and a quark which can split into a quark plus a gluon. And so on. You can have many gluons. Gluons can emit more gluons. But the point is that in this theory, the relevant coupling constant is alpha strong. And the strong interacting coupling constant depends on the scale at which you measure it. But let's say generously, at collider energies, you're lucky if you get alpha S to be 1/3. So if your expansion parameters powers of 1/3, that coupling constant is not very small. So if perturbation theory works at all, and it's not guaranteed it will, you have to work very, very hard to use it. So do not do a leading order calculation in QCD and expect it to describe data at all. Expect to need to go to next to leading order and next to leading order and to have to do logarithmic resummations of all kinds of things. Low order descriptions in perturbation theory are not a good approximation to the real world of nuclear physics. That's the simplest thing that can go wrong. The second thing that can go wrong is one that we do not like to talk about very often, which is the fact that the perturbation series usually does not converge. We like to pretend that that series is nicely convergent, and if I have a small enough coupling constant, then I can calculate to arbitrary precision 5,000 decimal places as long as I'm a good boy and work hard enough. Life doesn't work that way, folks. Usually, the perturbation series is an asymptotic series. Not a convergent series. Let me illustrate what that looks like. I have a nice figure in the notes that I'd like to share screen and show you. This was very eye-opening for me the first time that I saw it. Where are the notes? I thought I put the notes. Oh, I didn't put them on top. Okay, Canvas. So here's an example of a function that you might want to try to expand in perturbation theory. It looks a lot like the anharmonic oscillator, the quartic correction to the harmonic oscillator. So you have some integral. You're integrating dy from minus infinity to plus infinity. In the exponential, you have a nice Gaussian factor. Kind of looks like the potential energy of a harmonic oscillator. It's nicely convergent. I'm adding to that a quartic term with some coupling constant lambda. I can integrate this function exactly. I can also approximate it in perturbation theory. I can imagine that that lambda is small, and I can decompose it in a series. If I decompose it in a series, I have various powers of lambda and y that enter the integrand, and a nice Gaussian factor that guarantees that every term converges when I do the integral. And so if I do this, I can plot the answer as a function of that coupling constant lambda. And something really screwy happens. So this black curve is the exact solution if you integrate the whole thing, including the quartic and the exponential. So if I start doing Perturbation theory, I approximate it at second order in perturbation theory. That's this dark red curve. You see that at low values of the coupling constant, it describes the exact solution well, and at a certain point, the corrections start to grow, and it's not a perfect description. When you go from second order to third order perturbation theory, it gets a little bit better. When I go from third order to fourth order in perturbation theory, it gets a little bit better for a while. All the curves are really close together here, but if you look closely, you see that that brown curve is a little bit underneath the red one. It's a little bit closer to the real answer until at a certain value of the coupling constant, it stops being an improvement and it starts getting worse. Here in this region, fourth order in perturbation theory is a worse approximation than lower orders was. And from fourth order to fifth order and from fifth order to 10th order, the situation just gets worse. So in this case, the harder you work and the more terms in perturbation theory you calculate, the worse an approximation you get. So you see that this starts to break down and describes the curve less and less. And the more terms you keep, the earlier the problem happens. So by the time you get to 10th order, the approximation is breaking down at lambda of, 0.2, as opposed to second order, which was doing a fairly good job up to lambda of about 0.5. So this is the reality of perturbation theory. Most of the time, you are dealing with an asymptotic series that does not fully converge. So do not expect that if you calculate 500 terms in perturbation theory by spending your whole life on it, that that's actually going to help. Usually calculating the first few orders in perturbation theory is a good description, and at some point down the line, that dragon shows up and rears its head, and your approximation starts to fail. So this is another thing that can go wrong in perturbation theory. This is closely related to another important point, which is that there can be genuinely non-perturbative transitions that your perturbation series will never capture. So scenario 3, non-perturbative physics leads to non-analytic dependence on the coupling constant G. There's a notorious example in mathematics of an essential singularity. If I have a function of G, and that function is e to the minus 1 over G, and I want to take a series expansion around G equals 0, now, okay, fine. G equals 0 is a little bit weird because it changes from diverging one way to diverging another way when G goes to 0 from the positive side or the negative side. So for the sake of concreteness, let's say it's going to 0 from the positive side. I would like to be able to take this function of G and expand it in a Taylor series. I would like to write it as f of 0 from the right plus G times f prime of 0 from the right plus 1/2 G squared f double prime of 0 from the right, and so on and so forth. But when I take derivatives of this thing, I get some powers of G in front, and then I take the limit when G goes to 0. When I take the limit as G goes to 0, that exponential blows up to e to the minus infinity. And that e to the minus infinity coming from this exponential totally overwhelms anything that happens in the prefactor. So when you do this series expansion, every single term in the Taylor series is 0. So this is called an essential singularity. It is a singularity so strong that nothing you can do can touch it. This is such a strong singularity, it cannot be expanded in a Taylor series. So if your true Hamiltonian, your true interaction contains some dependence on G that looks like this, and your strategy is, I'm going to compute everything in a Taylor series, you will never be able to reconstruct dependence on G of this type. This is generally called non-perturbative effects, and there are many examples in physics that lead to exactly this kind of effect that cannot be captured in perturbation theory. Generally, when something radical and non-analytic like this happens, that is associated with a major transition in the degrees of freedom of a system. associated with a major realignment of the degrees of freedom. Let me give you two examples. One of them is the onset of superconductivity. Where you go from a theory in terms of electrons and maybe in solid state physics, a theory of holes, into a theory that is described by Cooper pairs. These are fermionic spin 1/2 degrees of freedom. These are paired up fermions that act like a single composite boson. And those bosons allow them to Bose condense and create the superconducting state. That jump in your degrees of freedom between electrons and Cooper pairs is non-analytic. It cannot be captured in perturbation theory around the electron ground state. Another example relevant to nuclear physics is the generation of the proton mass. You can go from a theory in which you have quarks and gluons which are massless, m equals 0. Forget the Higgs boson, we don't need it. A theory in which you have exactly massless quarks and gluons will create out of nothing a proton whose mass is 1 GeV. So, sorry, particle physics, we don't need the Higgs boson to create mass in the universe. 99% of the mass in the universe is associated with a chiral phase transition that takes you from massless QCD degrees of freedom to hadronic degrees of freedom, protons, neutrons, pions that are made out of some combination of quarks and gluons and generate the vast majority of their mass purely from the energy of the interactions. To illustrate this, if you look up online or take a class in solid state physics, then you can write down the BCS theory of superconductivity. And in that theory, you can solve for what the mass gap is. So this is essentially the binding energy of a Cooper pair. And when you solve that theory for what the energy is, you find that that binding energy, the mass gap, is 2h bar times the Debye frequency e to the minus 1 over the interaction potential times the density at the Fermi surface. I'm not going to bother defining most of these terms. The only thing that's important for this statement is this. You have a very weak, low strength interaction that effectively attracts one electron to another. That creates a non-analytic dependence that generates this mass gap. If you started with the theory of electrons and how they talk to each other by perturbation theory, that coupling constant V0 will never successfully reconstruct the non-analytic dependence that generates binding of Cooper pairs. So if you want to write down the BCS theory of superconductivity, you cannot do it in regular perturbation theory. You need non-perturbative approaches to describe this, such as the Hartree-Fock mean field self-consistent approximation. You need non-perturbative approaches. So these are usually the worst things that can happen to your perturbation theory when it's not going to work. You encounter a case when you get to high enough order in the series that you realize that it's not converging, it's only an asymptotic series. You have genuinely non-perturbative effects that you cannot capture in the series. Maybe your coupling constant is not small enough, so you have to calculate many orders to even get a decent comparison. There is one case which is similar to this onset of non-perturbative effects, but that we can deal with. And that is the case of degenerate perturbation theory. So I see I only have 10 minutes left, so I will probably set up the discussion here and we will not work all the way through the example that I have. So scenario 4 is closely related to scenario 3. This is the case when H0 is degenerate, but the perturbation GH1 breaks that degeneracy. The idea is that in that degenerate subspace of your bare Hamiltonian, there are many equivalent bases that you could pick. There's an infinite number of bases for that degenerate subspace. Most of them, however, will not be a good basis for describing the perturbation. And if you make the wrong choice to describe H0, then when I turn on the coupling, even a small amount of coupling, that basis radically changes. That would lead to non-analytic dependence, which could not be captured in perturbation theory. But there is a good choice. The bottom line is if you find the basis of that subspace in which the perturbation is diagonal, that basis is stable under the perturbation. And in that basis, you have a nice smooth analytic dependence on the coupling constant. So the punchline is going to be diagonalized perturbation in that degenerate subspace. This is a good basis for doing perturbation. So in the remaining few minutes, let's set up an example that will illustrate this. All right, so if I have an electron in the Coulomb potential, as in the hydrogen atom, I'm going to talk about one particular degeneracy here. It's degenerate in the z component of orbital angular momentum, and it's also degenerate in the spin degree of freedom. But now suppose we introduce a perturbation to the Coulomb potential. This is part of the fine structure of the hydrogen atom, which is spin-orbit coupling. That spin-orbit coupling breaks this degeneracy. So to be explicit, I'm talking about the case when my bare Hamiltonian is p squared over 2m minus e squared over r, the Coulomb potential. And my perturbation theory, my perturbing Hamiltonian, is some coupling constant g times L dot s. Spin orbit coupling. So first, let me illustrate the statement that this spin orbit coupling breaks the degeneracy. In terms of a basis of states, so for the sake of discussion, let's take just the L equals 1 and spin 1/2 cases. So now I'm talking about a 6-dimensional space of LZ and SZ. So I'm taking LZ equals +1, 0, and -1. SZ is +1/2 and -1. So in terms of these things, I can rewrite this perturbing Hamiltonian GH1 as G times 1/2 L plus S minus plus 1/2 L minus S plus LZ SZ. I split up the dot product into X, Y, and Z. X and Y I convert into raising and lowering operators. The Z piece I leave alone. So this part is something on the diagonal of LZ and SZ. These are transition-inducing operators that cause you to jump levels. So the point is, in this basis, the Coulomb potential is diagonal. So if I write down a basis of states let's say, N LZSZ. So N plus 1 plus a half, N plus 1 minus a half, N 0 plus a half, N 0 minus a half, N minus 1 plus a half, N minus 1 minus a half. If this is my basis of states, then when I hit it with the bare Hamiltonian, this thing is totally diagonal. I get an energy En that depends on N, but none of the rest of that stuff, times an identity matrix, 1, 1, 1, 1, 1, 1, times the same matrix of states back. This is diagonal. H naught is diagonal. But the perturbation on that same basis of states is off diagonal. N1 half, N1 minus 1 half, N0 1 half, N0 minus 1 half, N minus 1 1 half, N minus 1 minus 1 half. And if I work out the matrix elements of this Hamiltonian on that basis, I get an overall factor of G H bar squared. And the business part of it is 1 half minus 1 half, 1 over root 2, 1 over root 2, 0. 0, 1 over root 2, 1 over root 2, minus 1 half, 1 half. Okay. So everything that I've not written here explicitly is 0. These things break up into nice blocks that are associated with the total z component of angular momentum jz. So the point here about the changing degrees of freedom is that for H naught, which is the case G equals to 0, H naught only, if I pick out one of these states, for instance, how about this one? The state N1 minus 1 half is a stationary eigenstate. For any G not equal to 0, it is not a stationary eigenstate anymore. So it doesn't matter how infinitesimal G is. As soon as I turn G to anything which is not 0, this state suddenly becomes unstable. That is a non-analytic dependence that cannot be expanded in a Taylor series. So if I try to solve this problem in this basis, I'm going to get divergences. Things are going to fall apart associated with trying to describe what happens to a state like this that falls apart the moment you turn the perturbation on. Instead, we need to go to a better basis, a basis in which this matrix is diagonal. This matrix is the identity matrix. I can transform to any basis I want, and the identity matrix stays the same. But if I go to a basis in which this one is diagonal, I solve this problem. This change in degrees of freedom is associated with this perturbation breaking that degeneracy. So if I start with a basis in which this perturbation is diagonal, that dependence will be smooth and none of my states will fall apart. So obviously that basis will be the total angular momentum basis, and we will work that out next time. We will show how by diagonalizing this, you can apply regular perturbation theory to it, and that will be the start of our discussion on the fine structure of the hydrogen atom. Okay, I'm out of time. Any questions or comments? All right, thank you guys very much. I'll see you on my... Yes, sir. Yes, sir. It's on Canvas. I realized that I didn't put it at the top of the list. Here, let me share it for a second. It is not published. You're right. I didn't click the thing. Sorry about that. There. Yes, now it is visible. My mistake. Sorry.
Thank you, Professor.
All right. Thank you guys very much.
Thanks.